Welcome back. Today we're going to continue our lessons on thermochemistry. We're going to start by doing a review of Hess's law, which we covered in the last video. Let's get started. All right, so the first thing we want to do for a Hess's law problem is take a look at our goal reaction and then the two given reactions. Remember, we're trying to find something in the given reaction that is the sole source or the sole provider of that element or compound in the main reaction or the goal reaction up here. So let's see, I'm looking at carbon monoxide in the goal reaction, and I see carbon monoxide is in reaction number 1, but it's not in reaction number 2. So that means that reaction number 1 is the main source or the sole provider of carbon monoxide for this reaction. So we're going to try and manipulate reaction number 1 so that it looks like the goal reaction in terms of carbon monoxide, that is. So up in the goal reaction, carbon monoxide is on the reactant side, and there's only 1 mole of it. So if we look at reaction number 1, we have only 1 mole of it, which is great, but it's on the product side, and it's supposed to be on the reactant side. So what we're going to do is just rewrite reaction number 1, but we're going to flip it. So we're going to have the carbon monoxide be on the reactant side. And then we're going to have the solid carbon. Remember, state of matter is really important for these thermochemical equations. So plus 1/2 of oxygen. Now, since we flipped the reaction, that means that we need to change the sign of our energy, okay? So when we write our energy this time, our delta H is going to be positive 111 kilojoules per mole. All right, so that takes care of reaction number 1. This is now changed, which means we're not coming back to it. Okay, so now if we look at our goal reaction up here, we've got oxygen. Reaction number 2 has oxygen, but so does reaction number 1. So we can't base anything off of oxygen because neither of our reactions are the sole provider for oxygen. We've got carbon dioxide, which we see here in reaction number 2, and it is not in reaction number 1. So carbon dioxide comes from reaction number 2. That's the sole provider. We have 1 mole of it, and it's on the product side, just like in the goal reaction. So that means that reaction number 2 is already set up the way that we want. So now all we have to do is go through and start canceling out things. So we've got 1 mole of carbon on the reactant side of reaction number 2, and we have 1 mole of carbon on the product side of reaction number 1. And that makes sense because there's no carbon in the overall reaction. Okay, now let's see here. We have 1 mole of oxygen on the reactant side of reaction number 2, and we have 1/2 mole of oxygen on the product side of reaction number 1. So what that means is that this 1/2 on the product side is going to be canceled out by 1/2 of the oxygen on the reactant side. So there'll only be 1/2 left over. Okay, and then the carbon dioxide doesn't cancel out. There's 1 mole of it, just like there's supposed to be 1 mole of it. Okay, so now all we have to do is add up our reactions and our energy. If we look at the reaction, we're going to have the carbon monoxide gas on the reactant side plus 1/2 oxygen gas will be left on the reactant side. And then let's see, the carbon canceled out, this 1/2 of oxygen canceled out. That means that we'll have this 1 mole of carbon dioxide that will be left on the product side. And that matches our goal reaction up here. 1 mole of carbon monoxide plus 1/2 mole of oxygen yields 1 mole of carbon dioxide. So we're just going to add up our 2 energies that we have. That's going to give us a heat of reaction. So we're going to have delta H, and then remember to put Rx in so that that's the heat of reaction. And that's going to be negative 283. And then we need to put kilojoules per mole of reaction. And we know that energy is given off because this is a negative sign, and that means that this is an exothermic reaction. So it's going to release heat. All right, so hopefully that made sense to you. And we can move on to the next problem. So the first way that we talked about solving a thermochemical problem was with Hess's law. Now the second way that we're going to figure out how to solve a thermochemical problem is products minus reactants, okay? So we've got a new formula here that we're gonna make sure that we understand. Okay, and that's this right here. So the heat of reaction, this little degree symbol that we have here, that means under standard conditions, okay, which is 1 atmosphere of pressure and 25 degrees Celsius. That's standard conditions. All right, this symbol right here, that's sigma, that's capital letter sigma in the Greek alphabet, and it means the sum, okay? It means to add everything up, okay? So sigma means to add things, all right? So we want the sum of the heats of, or the energy of all of the products at, standard conditions, minus the sum of the heats of, or energy of, all of the reactants at standard conditions, okay? Now for our purposes, all of our stuff is gonna always be under standard conditions. We're not gonna change that. You've got your formula there, and then it says multiply delta heat of formation by balancing coefficients in the reaction for an element or compound. This is the same thing that we've been doing. If you have to multiply your reaction through by 2 because of a balancing coefficient, then you need to multiply the energy by 2 because they're proportional to each other. So we've already talked about that. One thing that we do need to mention is that a single element or a diatomic molecule, remember diatomic molecules are anything that end in gen, okay? So that would be hydrogen, nitrogen, oxygen, or any of our halogens, okay? So that'd be chlorine, bromine, and iodine, okay? So all of those diatomic molecules, and then just any single element by itself. So if we had like solid iron, or if we had solid carbon, or like down here in this table we've got solid sodium, okay? So any just free element, that's what that's called, any free element or diatomic molecule, that's not going to have an amount of energy associated with it, okay? So that will always be 0 kilojoules per mole for the heat of formation because they readily exist that way in nature, all right? That's their lowest energy state, is to exist in that form. So there's no heat of reaction or heat of formation associated with them for that state, okay? All right, so over here on this side, we have our products, okay? And then, of course, on the other side, we have our reactants. And we need to sum the energies on both sides in order to plug them into our formula up here at the top, okay? So let's see here. We're gonna start with the product side. Get this word written, reactants. Okay, so we've got hydrogen over here on the product side. Remember, that's a diatomic molecule, so look down here in the table, 0 kilojoules per mole. I won't always give that to you, so you do need to remember that free elements and diatomic molecules have 0 heat of formation associated with them. So that hydrogen there has no energy associated with it, and then we have 2 moles of the sodium hydroxide, okay? The sodium hydroxide was negative 470 kilojoules per mole. But we have 2 moles of it up here as a balancing coefficient in our equation. So we're going to have 2 times negative 470 kilojoules per mole minus, okay, so that takes care of all of the products, okay, because the hydrogen doesn't count. So that's the products information from our formula up here at the top, okay? So we just accomplished that. Now we're going to minus, we need to do the reactant, okay? So I have 2 moles of liquid water in our reactant side, and that is negative 286 kilojoules per mole. So I have to multiply that by 2 because I have 2 moles of it in the balanced chemical equation. So 286 kilojoules per mole. And then we have 2 moles of sodium metal. But sodium metal is a free element, so there is 0 joules of energy for the heat of formation of that. So we don't take that into account. All right. So the heat of reaction, so delta H Rxn, okay, so the heat of reaction is equal to, and then we can just plug this into our calculator. So we've got 2 times negative 470 minus 2 times negative 286, and we end up with negative 368 kilojoules per mole of reaction. All right. So hopefully that's pretty easy to you. It's just the sum of the energy for the products minus the sum of the energy for the reactants. All right, let's try another one. Okay, so again, we've got our product side, we've got our reactant side, and we need to, add up our energies and multiply by balancing coefficients if necessary. So we have 6 moles of liquid water, all right? So the heat of reaction is going to be equal to products minus reactants. Okay, so we've got 6 times. All right, so here's liquid water, so that's going to be negative 286 kilojoules per mole. And then that's not everything for the products, all right? We also have 4 moles of gaseous nitrogen dioxide, so that's this one here. All right, so we're going to have plus 4 times, because we have 4 moles in our balanced chemical equation, so 4 times 90.37 kilojoules per mole. And this covers the product side of the reaction, okay? So I'm going to kind of put a big parentheses that groups both of those together, and this covers all of our products, right? So it's products minus reactants. So now we can do minus, and let's take a look at our reactants. So we have 5 moles of oxygen gas, but that's a diatomic molecule. It has 0 kilojoules for its heat of formation, so we ignore that. That leaves us with 4 moles of the ammonia. So we're going to have 4 times. The ammonia is the negative 46.19 kilojoules per mole. Make sure you include that negative 46.19 kilojoules per mole. And then we can just plug that into our calculator and get our answer. All right. Now, I know that probably y'all are screaming at the screen, like, what about sig figs? Well, let's see here. The lowest amount of sig figs was this negative 286, so we should only have 3 sig figs in our final answer, so I really shouldn't have boxed that yet. So we'll have negative, let's see, the first, second, third sig fig, always look 1 place value further for rounding, so that's going to be negative 1,170 kilojoules per mole of reaction. That's the real final answer. All right. Sweet. Let's see if you can figure out how to do this one on your own. I'll give you about 10 seconds on the screen, and if you need more time, just press pause, and then we'll work through it together and see if you got what I get. So we're going to do what we've been doing. We've got our product side, and then we have our reactant side. So we've got 2 moles of the carbon dioxide. Now, carbon dioxide, that's not a diatomic molecule, okay? That is carbon attached to O2. So that is an actual compound that needs to be accounted for. So we've got that energy right here. So it's going to be 2 times negative 393.5. I'm going to omit the units. I hope you'll forgive me on that. It's just going to save some time. So we've got 2 times that amount, and then we had 3 moles of liquid water. So we need to account for that as well. So it's going to be 3 times liquid water down here, still negative 286. Okay, so all of this is the products, right? So remember, it's going to be products minus reactants. All right, so we did the products minus now the reactants. Okay, so hopefully you remembered that oxygen was a diatomic molecule and it has 0 energy. So you don't include that. Notice that I didn't put it down here in the table, which is a pretty big clue that you aren't going to be using it because it's not in the table. All right, and then the next thing that we have over here is our ethanol, and we only have 1 mole of that, so that's negative 287 kilojoules per mole, and that is our reactants. All right, so that gives me delta heat of reaction is equal to negative 1,358. And then our sig figs, it looks like we are only having 3 sig figs here. So first, second, third, look 1 place value for rounding. So that means that we get negative 1,360. And then we've got kilojoules per mole of reaction. And that would be our final answer. All right, take a second, like another 10 seconds, and see if you can figure out how to do this one. All right, so if we look at this one, we see we've got our product side over here, we've got our reactant side over here. Now, if we look at our math, we've got 6 times carbon dioxide is negative 393.5 plus we've got 6 moles of liquid water, so that's going to be 6 times negative 286. So all of this is our products minus, now, reactants. The oxygen, that's a diatomic molecule, so we ignore it. And then over here, we have hexane, which is not listed in our table. That doesn't mean that there's no energy associated with the hexane, however, okay? So the question here is calculate the standard heat of formation for the cyclohexane. So that's the thing that we're looking for. We are looking for reactants. Like, what is it? What is the cyclohexane? Remember, the oxygen doesn't count. And all of this has to add up to be negative 3,924 kilojoules per mole. So this is basic algebra. Our variable is R. We're solving for R right now. So let's see here. We can go ahead and figure out what all of this stuff here is for our product side. And I'm getting negative 4,000 4,077 for that number. So negative 4,077 minus R, the reactants, the cyclohexane that we care about, equals negative 3,924. Okay, so we're trying to get R by itself. So we can go ahead and add the 4,077 to both sides. And that means that negative R is equal to positive 153. But I don't want to know what negative R is. I want to know what just R is, right? The amount of energy for R. So that's going to be negative 153 kilojoules per mole. Now, one tiny little detail that we need to make sure that we're aware of. This asked me to calculate the heat of formation for cyclohexane, not the heat of reaction. So it's just negative 153 kilojoules per mole. It's not negative 153 kilojoules per mole of reaction, okay? So when we put kilojoules per mole of reaction, that's when we're calculating a heat of reaction. If we're calculating a heat of combustion or heat of formation, then it's just kilojoules per mole. Okay, let's look at this last one here, all right? And let's do this one together, just so we can kind of speed things up a little bit here. So we've got our product side, we've got our reactant side, and we are trying to figure out what the heat of reaction is this time. Okay, so that's going to be products minus reactants. So for the product side, we've got 1 mole of sulfur hexafluoride, which is this right here. Okay, so that's going to be negative 1,209.0 kilojoules per mole, plus 2 times our hydrofluoric acid. So 2 times gaseous hydrofluoric acid. Not that there's another version of it in the table, but there could be, so make sure that you're paying attention to state of matter there. All right, so we've got 2 times negative 273.3 kilojoules per mole. Okay, so all of this takes care of our products. And remember, it's products minus reactants. So products minus. Now, on the reactant side, fluorine gas, that's a diatomic molecule, 0 energy, so we can ignore that. And now we've got our hydrosulfuric acid in gaseous form. So we want to pay attention to this one right here. All right, so we've got minus, there's only 1 mole of it, so minus negative 21.0 kilojoules per mole. And that's our reactants. Okay, so now we can plug all of this into our calculator. I'm getting negative 1,734.6. Let's look at our sig figs. So we've got 5 sig figs here, we've got 4 sig figs there, and we have 3 sig figs here. So we only want 3 sig figs. So that's 1, 2, 3. 1 place value further for rounding. It doesn't do anything, so this stays the same. So we get negative 1,730 kilojoules per mole of reaction, because we're calculating a heat of reaction this time. All right. So I hope that all of this made sense to you. This was our second way of working a thermodynamic problem, a thermochemical problem. The first way was Hess's law. The second way is products minus reactants. If you want to subscribe to the channel, you can click here. And if you would like to watch the next video in the series, you can click up here or take a look at the playlist right there. Thanks for watching. Bye.